Hello everyone, welcome to the channel Statistica Hub. So in this lecture we are going to study about subspaces. Okay, so firstly let's see what are linear combinations. Linear combinations. Okay, let's see it. So if I said that V be a vector space over K, over the field K, then a vector V which is in V vector space, a vector V in vector space V is a linear combination of vectors u1, u2 to um in V if there exist scalars a1, a2 to am in K such that V can be written in their linear combination as a1 u1 plus a2 u2 plus am which is also can be written as sigma I going from 1 to m ai ui, where ai's are what? Ai's are scalars. Okay, so this is what we said the linear combinations are. So here, let V be a vector space over the field K, then the vector V in the vector space V is a linear combination of the vectors u1, u2 to um in the which are also in the vector space V if there exist scalars a1, a2 to am, a1, a2 to am. Then the linear combination, then the vector V can be represented in the linear combination of the vectors u1, u2 to um. This is what we said the linear combination is. Okay, so this is the linear combination. Now we'll see what are the spanning sets. Spanning set. Spanning set. So V be a vector space. We're going to consider vector space over a field K in every definition. Okay, so let V be a vector space and vectors u1, u2 to um in this vector space V are set to span V, or we can say that these are the generating set or spanning set of V. What? Spanning set of V if every v every vector V which belongs to this vector space V is a linear combination of u1, u2 to um if there exist scalars a1 to am. Okay, so here what we said is that the set of vectors u1, u2 to um, this is the set of vectors will span V if will span V or will generate V, or the spanning set of V if every vector which is belonging to the vector space V can be written in their linear combination, which is av equals to a1 u1 plus a2 u2 plus dash dash am um. Okay, now let's see the general remarks of this. Let's say if I say that u1, u2 to um are the set of vectors which will span V. Okay, and there is any other vector which is W. Then the set of W with u1, u2 to um will also span V. Will also span V. By spanning of V, we mean that it will generate the whole vector space V, that every element of V can be written in their linear combination. Okay, now let's see some examples of these. Okay, now let's say I have the vector space V which is R cube. This is my vector space. Okay, and E1, the set of elements 1 0 0, E2 which is 0 1 1, E3 which is sorry 0 1 0, E3 which is 0 0 1. This set of vectors form the spanning set of V. What? This is forming the uh, form spanning set of V. Spanning set of V. So if I am saying that these set of vectors are spanning the vector space V, then there is a vector V which belongs to this vector space that can be written in their linear combination. Okay, let's say I have a vector V which A, B, C. This is my vector. Okay, then this can be written in their linear combination, which is v equals to x e1 plus y e2 plus z e3. Okay, uh, let's say I have these x v vector. Let's give them their value, any value. 5 minus 6 2. Okay, now how can I represent this? So for getting the linear combination, I have to find the value of the scalars, which is x y z, that are belonging to the field of scalars. Okay, so firstly I have to find the value of the scalars to get a proper linear combination. Okay, 5 minus 6 2, which is equals to x 0 sorry 1 0 0 plus y 0 0 1 0 1 0 plus z 0 0 1. Okay, so from this I get that x equals to 5, y equals to minus 6, z equals to 2. Okay, this is our value of scalars. So the v vector can be represented as 5x plus 5 e1 plus minus 6 e2 plus 2 e3. Okay, this is the set of vector, this is the our linear combination here. Okay, now let's see another example of this. Let's say I have a vector space on the r cube. This is my vector space r cube, and the spanning set is w1, which is 1 1 1, w2, which is 1 1 0, and the third vector is 1 0 0. This is my spanning set. Okay, so this is my spanning set, which is spanning v. Okay, this is spanning v. So if this is spanning v, then there is a vector v which belongs to this vector space, and that can be written in their linear combination. So this vector space v equals to x w1 y w2 plus z w3, which is equals to, let's say I have a vector v which is equals to a b c, a b c. Then I have to find the value of the scalars first. Let's find that. X 1 1 1 plus y 1 1 0 plus z 1 0 0. Okay, let's simplify this. ABC, which is equals to x plus y plus z, and here it is x plus y, and here it is x. So from simplifying here, we get x equals to c, and the second equation is v equals to x plus y, and the third equation will be a equals to x plus y plus z. Okay, so we get the x equals to c from this. By substituting, we got y equals to b minus c, and z equals to a minus b minus c, which is z equals to a minus b. So our linear combination, we got v equals to cw1 plus b minus c w2 plus a minus b w3. Okay, so this is our linear combination here. Now let's see the concept of subspaces. Subspaces. So for a vector to be a subspace, what should it satisfy? Let's see that. Let V be a vector space over K. Over the field K, this is a vector space. Okay, and let W be a subset of V. Let W be a subset of this vector space V. Then W is a subspace of V. W is a subspace of V if W is itself a vector space. What? If W is itself a vector space over the field K. The point to remember here is that the vector space V is also on the field over K, and the vector space, the subset of W, also has to be the over the field K. Matlab, they has to be on the same field. Okay, they has to be on the same field. So W is itself has to be a vector space over K with respect to vector addition and scalar multiplication. Now let's see the simple criteria of checking whether W is a subspace or not. There are simple criteria to check. First, 0 should belongs to the W. The vector 0 should belongs to W. Second thing, if u comma v belongs to W, then the addition, which is vector addition u plus v, should also belongs to W. And third one is scalar multiple, which is k belongs to the scalar k, then ku, the scalar multiplication of k by with the vector u, should also belongs to W. And the single condition of checking second and third is that if I have u comma v belongs to W and the a comma v which belongs to the field of scalars, then their linear combination, which is au plus bv, also belongs to W. Okay, so this is the concept of subspaces, that for a vector to be a subspace, which is a subset of, it has to be the subset of vector space V, and it should satisfy the property of that 0 belongs to W, 0 has to be in that, and vector addition and scalar multiplication. Okay, now let's see that for every vector space V, the entire space which is V, entire space V, that vector space itself is always a subspace of V. That vector space, let's say, write it here. Vector space V, okay, vector space V, that is the entire subspace V, is always a subspace of V. It is always a subspace of V, and this is called improper subspace. What? Improper subspace, because we are considering here the whole vector space. That's why it is called improper subspace. Okay, and other than this are called proper subspaces, except one, which is the set containing of null vector, the set containing of null vector of V, that also forms a subspace of V, and these are called trivial subspace of V. What? Trivial subspace of V. Okay. Now let's see that if I'm saying that V is a vector space over the field of real function, that it is a vector space of all real functions from R to R, all real functions, then f of minus x equals to f of x. This is what? This is an even function, and f of minus x equals to minus f of x. This is what? This is an odd function and continuous function. These all form the subspaces of vector space. These all form subspaces of vector space over R. Okay? Even function, odd function, and continuous function, these all form. This is the basic example I have given here. Okay, now let's see it more deeply, we'll understand it more clearly. Let's say I have u, which consists of all vectors in R cube. Okay, and u can be represented as a, b, c, which is a equals to b equals to c. This is my u. Okay, so what are the vectors in U? The vectors in U are like 1, 1, 1, 2, 2, 2, and 7, 7, 7. These are the vectors in U. Now I have to check whether U will form a vector space subspace or not. Okay. So for a subspace, what the condition is that 0 belongs to W. Then if I check 0 vector, which is 0, 0, 0. Yes, it 0, 0, 0. It is belonging to U, and if I take U, which is a, and V, which is b, 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 then their sum, which is U plus V, equals to a plus b, a plus b, a plus b. Then their sum is also belonging to U, also belonging to, and the scalar multiplication, which is ku equals to ka, ka, ka. This is also belongs to U. So this is forming a, U is a subspace. This is forming a subspace. Subspace of R cube. Okay. Now let's see one more. That if I say that V equals to R's power n R, this is our vector space. This is our vector space over the field R. And W is defined as x1 to xn, which belongs to R's power n, such that a1 x1 plus a2 x2 equals to an xn equals to 0. So this will form a subspace. It will always form a subspace. It will always form a subspace only if this combination is equal to 0. This combination is equal to 0, then it will always form a subspace, because 0 is the basic condition in a subspace, that 0 should all belongs to w. But if this is not equals to 0, then it will not form a subspace. Why am I saying that? That for this combination to be 0, the field of scalars became 0. Okay, so the 0 vector will appear here. Okay, if I do all the field of scalars 0, then if the linear combination is not equals to 0, then then our 0 vector will not belong here. Okay, will not belong here, because if I put any values of these scalars, then it will not equals to 0, because I have no vector 0 here when this linear combination is not equals to 0. Okay, so it will only form a subspace if the linear combination is equal to 0. And the set of real functions, if I have the set of a vector space of all real valued functions, then the set of all continuous functions, the set of all differentiable functions, these will form the vector spaces. How? Let's see this. Let's say I have the function f which belongs to the function space fx. Okay, and I have f of x equals to 0. F of x equals to 0, then it is forming a subspace, as it has function f of x equals to 0. Then there's some f of x plus g of x can be as f plus g of x. This is their sum, and this is their scalar multiple also. F alpha f of x equals to, sorry, alpha f x equals to alpha f of x. Okay, so this is satisfying all of the three conditions. That is why continuous functions, similarly you can check for the differentiable functions, they form the subspaces. Okay, now let's see an important property of subspace, which is the intersection of any number of subspace. The intersection of any number of subspaces of a vector space is a subspace of V. Subspace of V. That here I am saying that the intersection of any number of subspaces of V is a subspace of V. How? Let's see this. Let's say I am saying that U and WB are subspaces of vector space V. These are the subspaces of vector space V. Okay, so if I'm saying that they are the subspaces of V, then 0 belongs to U and 0 should also belongs to W. Then 0 is also belonging to their intersection. 0 is also belonging to U intersection W. And let's just check for the second condition, that if U and V belong to U intersection W. Okay, let's say U and V belong to U, and U comma V also belongs to W. Then AU plus BV also belongs to U, and AU plus BV also belongs to W. So AU plus BV also belongs to their intersection U plus W, U intersection W. So from this, here we get that this is satisfying all the properties of 0 vector, and second, which is the linear combination property, like the combination of second, third we have made here. Okay, this is the satisfying the condition of vector addition and scalar multiplication too. So this is a, so U intersection W is a subspace of V. Okay, now let's say that U intersection W is a subspace of V, but union of two subspaces need not be a subspace. U union W need not be a subspace. Okay, this will only form a subspace. Union of two subspaces is only a subspace if one is contained in other. If one is contained in other. Okay, how? That is, if let's say I have two sets which is w1 and w2, I have these two subspaces. Okay, and I want to find the union of these two subspaces, whether it is subspace or not. It will only form a subspace if w1 is subset of w2, or either w2 is subset of w1 if one is contained in other. Because if w1 is subset of w2, then w1 union w2 equals to w2, and it is a subspace of V. So it will form a subspace of V. So the union of two subspaces is only form a subspace of V if one is contained in other. Okay. Now let's see that if I have the vector space complex to complex. Okay. I have the vector space complex to complex. Then let's say I have another vector space complex to real, real to rational, rational to real, and real to complex. Then which one of the following is the subspace of this vector space complex to complex? Which one of the following is the subspace of this? Look at this clearly. So for the first condition I have said about the subspaces is that it that they have the same field. Okay, the field of this vector space is complex, and here we can see that the field of this only vector space is complex. But if you look at it clearly, that it is the field, it is the vector space real over the complex, that it is not a vector space. It is not a vector space because real does not form a vector space over the field of complex. Okay, so it is not forming a vector space, and these are forming the vector spaces. These all are forming the vector spaces, but these are not the subspaces of this complex to complex, because they have to be on the same field. But here it is on real, it is on rational, and it is on real. So I think you will get a brief understanding of this topic. Okay, now let's see it like this. If I have a vector space r cube to r, and a let's say I have a subspace which is x 0 0, where x belongs to r, and another w2 which is 0 y 0, which is y belongs to r. Then if I take union of them, if I take, oh, and my pen is not working. What is this? Huh? I'm sorry for this inconvenience, guys. Um, what is going on? Okay, so y is belonging to r. Okay, then if I take the union of these w1 and w2, then it will become x 0 0 or 0 y 0, where x comma y belongs to r. Okay, but the sum of these sorry, if I denote it as u, and denote it as v, and give them their values, u equals to 100, let's say, and v equals to 010, then their sum, which is u plus v, which is union, which is equals to 1110, which does not belong to w1 union w2. So from this we got a clear example of that the union of two subspaces need not be a subspace. Okay, now if we'll go about the matrices topic in this, then we can easily verify that the set of diagonal, what? Diagonal, or I think symmetric, skew symmetric matrices, skew symmetric, yes. These form the subspaces. These form subspaces. You can easily check them by the basic criteria of subspaces, which is vector addition, scalar multiplication, and zero vector. That has to belong to this. So diagonal matrices, symmetric matrices, and skew symmetric matrices, they are belonging to the subspaces. They form a subspace. Sorry. Okay. So now let's see another example, which is like very important. If I have a uh, S, which is set defined as x, y, z belonging to R cube, and x square plus y square plus equals to z square. Okay, and S is a non-empty set of R cube. What? R cube. Then we'll check whether S is a subspace or not. Okay, whether 0 comma 0 belongs to this S. Yes, 0 comma 0 is belonging to the subset of whether 0 square plus 0 square equals to 0 square. So it is belonging to S. Now let's check for the vector addition and scalar multiplication. Let's say if I take the vector alpha, which is equals to x1, y1, z1 belonging to S, and another vector v, which is x2, y2, z2 belonging to S, then their alpha plus beta, which is equals to x1 plus x2, y1 plus y2, and z1 plus z2. This is their vector addition. But if you look at like this, if alpha equals to this, then it means that x1 square plus y1 square equals to z1 square, and the vector beta means that x2 square plus y2 square equals to z2 square. And if I see it by the definition of S, that the addition of these has to be x1 plus x2 square plus y1 plus y2 square equals to z1 plus z2 square. But this is not the possible case always, that it may not be equals to this z1 plus z2 whole square. Let's say check it by an example. Let's I define alpha as, I give them values like 3, minus 4, and 5. And let's say beta, will give the beta the value minus 3, 4, and 5. Okay, now I will define alpha plus beta, which is equals to 0, 0, and 10, where we can easily see that 0 square plus 0 square will not be equals to 10 square. Okay, so this does not form subspace of R cube. Okay, now let's see the topic of linear sum of two subspaces. Okay, linear sum of two subspaces. Actually, the linear sum of two subspaces form subspace. The linear sum of two subspaces form subspace. How? Let's see that. Let's say I have two subspaces, which is U and W. These are subspaces over vector space V. Sorry, of vector space V over F. Okay, over field of scalars, whether you can say it K or F, whatever it is. Okay, so the linear sum of these two vectors we defined as U plus W, where U belongs to U and W belongs to W subspaces. Okay, this is said to be the linear sum of two subspaces. This is the linear sum of two subspaces. Now let's see how they form a subspace. How they form a subspace? If I say that alpha is a vector which belongs to this U, if alpha belongs to U, then alpha plus 0 equals to alpha. Alpha plus 0 equals to alpha, where alpha belongs to U and 0 belongs to W. So from this we get that alpha is belonging to U plus W. Okay, alpha is belonging to U plus W. This is what? This is the linear sum. This is the linear sum. We are taking the linear sum, which is U plus W. Okay, U plus W. So alpha is belonging to U plus W. So from this we got that U is a subset of U plus W. U is subset of U plus W. Okay, similarly, if I say that alpha is subset of W, then we can define alpha plus 0 equals to alpha as alpha is belonging to W and 0 is belonging to U. So from this we can get that alpha is subset of U plus W, and W is subset of U plus W. W is subset of U plus W. So from this we can clearly say that as U is subset of U plus W and W is also a subset of U plus W, so the linear sum of two subspaces is a subspace. This is what U plus W we define here is the linear sum of these two subspaces U and W, and we have already said that these are the subspaces. Okay, so these the linear sum of two subspaces is a subspace. These will form a subspace. Okay. Okay, so now there is an one important topic in subspace, which is in matrix form, in matrix topics actually. Let's see it here only. That if we'll see about the homogeneous system of the equations. Okay, if I see the homogeneous system of the equations, then homogeneous system of equations. If I see those, then what is a homogeneous system? It is Ax equals to 0 with n variables. It has n variables. Then A is with matrix m cross n, and x with n cross 1 equals to 0. Okay, this is what we mean by Ax equals to 0. And let I say that the solution space of this homogeneous system of equation, which is this have n variables, this must have n unknown values, which is x1 x2 to xn, which belonging to the field of scalars, because it is the solution space. Okay, so I have to know that whether this solution space will form a subspace or not. Okay, of the field of scalars case power n. I want to know this. So we'll check this. Let's check. So first we'll check whether 0 belongs to W or not. 0 belongs to W or not. That Ax equals to 0. This is our equation is, if the solution is 0, that is A dot 0 equals to 0, it will become to 0. So 0 vector exists. Zero vector is existing. Zero solution is existing in homogeneous equation. Second, we'll check if U comma V belongs to W, and U and V are solutions. Let's say U and V are solutions of Ax equals to 0. Okay, the system of homogeneous of equation has U and V as a solution. Then AU equals to 0. That means X is equals to U and X is equals to V, which is AU equals to 0 and AV equals to 0. Now, if I am saying that U comma V belongs to W and AB, which is the field of scalars, it also which belongs to the field of scalars. So now let's check A of the linear combination of this AU plus BV. This is the value of X here. This is our solution here. Okay. So this AU plus BV, the linear combination which we'll check for the subspace is whether this A of AU plus BV is equals to 0 or not. So A of AU plus B of AU equals to A dot U plus B dot 0. Sorry, A dot 0 plus B dot 0, as we have defined here, that if U is the solution, then AU equals to 0. If B is the solution, then AV equals to 0, because it is a homogeneous system of equation. That's why we are taking A equals to 0, because it is the equation. Homogeneous system has this equation Ax equals to 0. So which is equals to 0. So AU plus BV belongs to this W. So from this we get that it is satisfying the properties of subspaces. So this is a very important property. Like it's very important. We are going to use it many of the times, that homogeneous system, in homogeneous system, that the solution space of homogeneous form subspaces of case power n. Okay, what? That the solution space of homogeneous form subspace of case power n. This is very important. Okay, so this is the what we have studied about the subspaces. Now let's see in the next video other topics of the subspaces. Okay. Thank you.